Okay. Today we start. Today we start with the computer network. Next topic under Prerna scheme lectures from ACT Nagpur. So last time we study about the uh, routing algorithms and comparison of virtual circuit and datagram networks. So routing algorithms. So there are routing algorithm can be grouped into two major classes. First is non-adaptive, that is we call static routing, and second one is adaptive, that is we call dynamic routing. So non-adaptive algorithm so base their routing decision on measurement or estimates of the current traffic and topology. Instead, the choice of the route to use to get from I to J is computed in advance. So offline and downloaded to the routers when the network is booted. So this procedure is sometimes called static routing. Now, whereas the adaptive routing, in contrast, change their routing decision to reflect changes in the topology and usually the traffic as well. So, adaptive algorithms differ in first regarding information, that is example is locally or from adjustment of routers or from all routers that we get the information. Then when they change the routes in every t seconds when the load changes or when the topology changes. So what metric is used for optimization? Example is distance, number of hops, estimated transmit time. So this procedure is called dynamic routing. So different routing algorithm which are used here. First is optimality principle. We study already. Now today we start with the shortest path algorithm, then flooding, distance vector routing, link state routing, and hierarchical routing. So shortest path routing we also call DJ extra. So the idea is build a graph of the subnet with each node of the graph representing a router and each arc of the graph representing a communication line or link. So to choose a route between a given pair of routers, the algorithm just finds the shortest path between them on the graph. So what is the procedure to find the shortest path route? So first start with the local node. We also call a router as the root of the tree and assign a cost of 0 to this node and make it first permanent node. Second is examine each neighbor of the node that was the last permanent node. Now third procedure is assign a cumulative cost to each node and make it tentative. So how it happens, let's see in next slide. Among the list of tentative nodes, first find the node with smallest cost and make it permanent. If a node can be reached from more than one route, then select the route with the shortest cumulative cost. Now repeat the step to finding the permanent node. Repeat step 2 to 4 until every node becomes permanent. So example is given here. There is a router ABGECFDH. So cost is given for distance between two routers. So first start with the node A. If you start, there are two nodes B and G. The cost of G is 6 and cost of B is 2. So smallest cost is 2. So we can adopt the B with distance 2 from A. Now from B there are two nodes again, that is E and C. So from A, that Cn is infinity. So we can move from A to B. So from B, again we find that from A there are two nodes, that is G and B. So first we can accept the B and then directly G. So that is shown in that diagram. So from B there are two costs. A to C, we can find that 2 plus 7, that becomes the 9. From A to H, again the value becomes A to F, the value becomes 2 plus 4 6. And from G we can accept. So from E, again there is a smallest, there are two nodes C and H, in which the value is 6 is small, so we can consider it. So the distance of H from A is 2 plus 4, 4 plus 6, 8. So that is a value. So this is the execution of Dijkstra's algorithm, in which the example is given. So which node is become permanent and which node becomes the tentative. So initially first node is permanent and remaining three nodes, that is 2, 3, 4 are tentative. So here, two out of 2, 3, 4, we find that the distance of 2 and 3 and 4 is 3. Distance of node 2 is 3. Costing of node 3 is again 2, and costing of node 4 is 5. So out of which smallest cost is of 3. So we can make it 3 as a permanent. Now from 3 again we find the tentative nodes, that is 2, 4 and 6. The value of 2 is again 3. The value of 4 is again 4 and value of 6 is 3. So out of which the minimum cost is 3. So we can get any two. So value of 5 is infinity at that time. So we can make 3 as a permanent. So 1 to 3 becomes the permanent. Tentative nodes from 3 is 4, 6, 5. The cost of each is given for fourth node, that is 4. For fifth node is 7 and 6, 3. So out of which 3 is smallest cost. So we can consider it 3. 6 is the smallest cost. So permanent nodes are 1, 2, 3, 6 in the third steps iterations, and tentative is 4, 5. So out of 4, 5, the value of 4 and 5 is again 4 is small, so we can make it permanent, and remaining tentative is 5. Now 5 at last becomes the permanent. So thus we can find the root. Now next is a routing is flooding. So another static algorithm is flooding, in which every incoming packet is sent out on every outgoing line except the one it arrive on. So flooding is obviously generates vast numbers of duplicate packets. In fact, an infinite number unless some measures are taken to damp the process. So one such measures is to have a hop counter contained in the header of each packet, which is decremented at each hop, with the packet being discarded when the counter reaches 0 ideally. The hop counter should be initialized to the length of the path from source to destination. So a variation of flooding that is slightly more practical is selective flooding. So in this algorithm, the routers do not send every incoming packets on every line, only on those lines that are going approximately right in the direction. So flooding is not practical in most application. So there are intra and inter-domain routing. If you consider, there are intra and inter-domain routing. An autonomous system we call AS is a group of networks and routers under the authority of single administration. So routing inside an autonomous system is referred to as intra-domain routing inside the autonomous system. Here we can use distance vector link state routing algorithms for that. So we see that routing between autonomous system is referred to as inter-domain routing. So we can consider path vector. So path vector routing is used in a autonomous system inside autonomous system. So each autonomous system can choose one or more intra-domain routing protocols to handle routing inside the autonomous system. However, only one inter-domain routing protocol handles routing between autonomous system. So there are two types of routing protocols: intra-domain and inter-domain. So distance vector and uh, link state is a example or types of intra-domain routing. Inter-domain further divided into path vector routing. So for distance vector, we can use RIP protocol. For link state, we can use OSPF protocol. So for path vector, we can use BGP protocol. So let's see. So distance vector routing means in distance vector routing, the least cost route between any two nodes is the route with the minimum distance. In this protocol, as name implies, each node maintains a vector or a table of minimum distances to every node. Mainly three things in this: initialization, sharing, and updating. So in initialization, we see that each node can know only the distance between itself and its immediate neighbors, those directly connected to it. So for the moment, so for the moment, we assume that each node can send a message to the immediate neighbors and find the distance between itself and these neighbors as shown in figure. For the initial table for each node, the distance for any entry that is not a neighbor is marked as a infinite, that is unreachable. Let's see. Initialization of tables, distance vector routing. So costs are given here for costs are given here. In this cost, for each node, from each node, the distance of all the nodes, that is from A to B, A to C, A to D, A to E, the cost is given, and thus we can make each tables, each nodes table, that is A stable, D stable, C stable, and B stable, and E stable. Let's see. From A to A, the cost is distance is 0. From A to B, cost is in the diagram is given, that is 5. From A to C, the cost is 2. Then from A to D, the cost is 3. And from A to E, there is an intermediate node. So the cost is infinity. So this is an example of initialization. So thus these table from D, the distance of each node is given in the table. So costing of A to D or D to A is 3. From D to B, the costing is infinity because there is an intermediate node. From D to C, again there is an intermediate node. Cost is infinity. From D to D itself, so cost is 0. And from D to E, again there is a intermediate node, that is ABC. So cost is infinity. Now we can make the table of C's tables. So from C to A, again cost is 2. From C to B, cost is 4. From C to E, cost is 4. Now C to C is 0, and C to D, there is an intermediate node. So cost is infinity. Okay. Now we consider B's table. Again here in B's tables, we find that the distance of A from B is 5. Distance of C from B is 0. Then distance of B to B is 0. Distance of C is 4 from B. And distance of D, there is an intermediate node. So value is infinity. Now distance of E from B is 3. Thus, each node have their table, that is initialization of tables in distance vector routing. Now, second stage is sharing. The whole idea of distance vector routing is the sharing of information between neighbors. Although node A does not know about node E or node C, so if node C share its routing table with A, so the node A can also know how to reach node E. So on the other hand, node C does not know how to reach node D. But node A does. If a node A shares its routing table with the node C also know how to reach node B. So in other words, in short, we say that nodes A and C as immediate neighbors can improve their routing table if they help each other. If they help each other. So make a note. In distance vector routing, each node share its routing table with its immediate neighbors, timely, periodically, and when there is a change in the cost. So this is about the sharing. So sharing, which can exchange their information, sharing which can exchange their information with each other. So example is a distance vector routing. Each node share its routing table with its immediate neighbors periodically, and when there is a change in the cost of table of a node. So this is about the second step, that is sharing of a table. So let's further see how we can find the shortest distance. So here updating. So when a node receives a two column table from neighbor, it's it's needs to update its routing table. Uh, so updating takes steps. First is the receiving node needs to add the cost between itself and sending node to each value in the second column. So we can say that is x plus y. If the receiving node uses information from any row, the sending node is the next node in the root. The receiving node needs to compare each row of its old table with the corresponding row of the modified version of the received table. Now, if the next node entry is different, so in that case, the receiving node chooses the row with the smaller cost. So if there is a tie, the old one is kept. B. If the next node entry is the same, the receiving node chooses the new row. So, for example, suppose node C has previously advertised a route to node X with distance 3. So, suppose that now there is no path between C and X. So, node C now advertises this route with a distance of infinity. So, infinity is the route, then there is a intermediate node. So, node A must not ignore these value even though its old entry is smaller. The old route does not exist anywhere. The new route has a distance of infinity. So updating. So initializing, sharing, now updating in distance vector routing. How that updating is done. So there is a cost of received from C. Now C is having a different cost. So A's modified table is given. So when we compare with the new table, so there is old table and new table. So if you compare with the A's modified table with the A's old table, so it can receive from C. So A's modified table is with the different cost and B's modified table. So out of which, if you compare in this diagram, we see that A's modified table and A's old table. So if you compare between them, so if you compare A's distance is 0, A's distance is 4, so smallest cost is considered. So in old table we consider 0 as compared to 4 is small. So in A's new table the smallest value we have to consider. Now next B's distance is given in both the A's modified table and A's old table. So 5 and 6, out of which 5 is small. So we consider the cost of B is 5. Now if you consider C in both the table, both having the same value. So we consider same value. Now infinity and 3. So we consider a smallest value, that is 3. Infinity is large. Now E, if you compare 6 and infinity, so we can consider smallest values as a 6 because infinity is large. So here when you update the tables, so distance can be changes here with the different cost. So if you consider this, so A is modified table and A is old table, so we find the new table with the minimum cost. So here there is a final diagram after modification of each table. So if you compare uh, modified table, so A to A, we consider only these A's table. For example, for final diagram, so to A, we start with the A and cost of A is 0 initially. Now when we move to B, that is node B from A, the cost is 5. If you move to C, the cost is 6. If you move from A to D, the cost is 3. If you move A to E, if you move A to E, smallest cost. So there are two paths, A, B, E. So 5 plus 3, 8, and A, C, E, 6. So both are out of which we consider the smallest path. So that is A to C and C to E. So this is a final diagram for each table. We consider the smallest path for comparing the distance. Now another there is a B stable, and there is a C stable, and there is a B stable and E stable. So we can find the routing table for each node. So this is a final diagram for shortest path. Now while sharing, when to share, though this is a question. The question now is, when does a node send its partial routing table? So only two columns to all its immediate neighbors. Okay. Now when to share, the question now is when to share. When does a node send its partial routing table, only two columns to all immediate neighbors? The table is sent both periodically and when there is a change in the table. So periodic update, a node sends its routing table normally every 30 seconds in a periodic update. The period, that particular time or period, that depends on the protocol that is using distance vector routing. Now triggered update. Yes. Now a node sends its two column routing table to its neighbors anytime. So there is a change in its routing table. Change in its routing table. So to its neighbors anytime. So there is a change in its routing table. So this is called a triggered update. It is also called a triggered update. So change can result from following way. So first, a node receives a table from neighbor and resulting in changes in its own table after updating. So second part is a node detects some failure in the neighboring links. So that links which results in a distance change to uh, infinity. So there is a periodic update and triggered update for finding the results. So thus a neighbor can change their updations. Okay. So using the results or using the different values. So node detects neighboring links. So this is a when to share. So before failure, what is two node instability? So example shows here. So there is a distance of or costing. So we start with the x, and after two costing of a to reach the a from x is 2, and from to reach b the value increases 2 plus 4 6 from uh, a. So after b receives update from a, after b receives update, so 6, so 6 and return to a again, it is 10, or if you consider 14, so it reduces with the value of 10. So after failure, x doesn't know this distance, so that can be described by b. After a receives update from b, now a gives a update, so that value changes. So both the values are, a doesn't know about b and b doesn't know about a, so the value is given, the cost value is becomes the infinity. So finally there is a two node with the instability, means he doesn't know the actual cost of the node, so it is called two instability. So after b receives update from a, so A becomes the failure. So what is the cost? And after A receives the update, now B becomes the failure. So when updates becomes uh, got by A, then B becomes failure, and B if update got by A, now the B becomes the uh, update and becomes a node with two nodes instability. Now, what is a three node stability? If you consider three node, A doesn't know about B, B doesn't know about C, and C doesn't know about A. So all these three nodes, after C sends to root A, so before failure, so diagram shows the value of A, B, and C. After failure, the A becomes the in with the infinity value. Then B after B seconds to root A, again after A seconds to root B and C, but the packets to be lost. So both the after C sends the root to B. So all the nodes A and B and C becomes the is, is in instability state. So it is called a three node instability. It is called a three node instability. So this is about the three node instability. Now there is a solution for instability. So how that solutions gives the results. So what is a infinity? First of all, we find that what is infinity. So redefine infinity to a smaller number such as 100. Suppose we consider 100 is a smaller number. Now for our previous scenario, the system will be stable less than 20 updates. Less than 20 updates. As a matter of fact, most implementation of the distance vector protocol define the distance between each node to be 1 and define 16 as infinity. So however, this means that the distance vector routing cannot be used in large system. The size of the network in each direction and cannot be exceed 15 hops. So split horizon is the strategy. Instead of flooding the table through each interface, each node sends only part of its table through each interface. So if according to its table, node B thinks that the optimum route to each X node is via A. So it does not inform information has come from A, taking information from node, modifying it and sending it back to node A. That creates the confusion. So in our scenario, if you consider our scenario, it does not need to advertise piece of information to A. The information from node A is modifying, so it sends to distance x. It sends to distance x. It sends to distance A. In this case, node A keeps its routing table to B. Node B also corrects its routing table. Now the system becomes stable after the first update. Both node A and B know that X is not a reachable. So So both node A and B know that X is not reachable. So split origin and poison reverse using the split origin strategy has one drawback. Normally, the distance vector protocol uses a timer, and if there is no news about a route, the node deletes the route from its table. When node B in the previous scenario eliminates the route to X form its advertisement to A, node A cannot guess that this is due to split origin strategy. That is, the source of information was A. So the split origin strategy can be combined with the poison reverse strategy. B can also can still advertise the value of X. So the distance with infinity is warning. So do not use this value. What I know about the root comes from you. Now this is a the count to infinity problem. So first we initialize all the nodes. 1 and 1 synchronize after one exchange. 2, 3, 4, 3, 4, 7, 6, 7, 8. So link state routing is based on the assumption. So it depends on assumption. That also the global knowledge about the topology is not clear. Each each node has partial knowledge. It's the state, and that is the type, condition, and cost of this link. In other words, the whole topology can be compiled from the partial knowledge of each node. Now let's see the table. A is a state of link. State of link means vertices which came and attach from which it gets. What is the cost of that vertices is given. So it's A is state till link, B is state of links, D is state of link, and E is dates of link. So with value that link is given. Now what is the building routing table? So creation of the states in the links by each node is called the link state packet. It's called link state packet. So dissemination of LSP link state packet to every each router flooding in an efficient and reliable way. Formation of shortest path tree for each node in an efficient and reliable way. So calculation of routing table is based on shortest path tree. Now creation of link state packet. A link state packet can carry a large amount of information. For the moment, we assume that its sequence number, age, first to node identity, and list of links. So these are needed to make the topology. The third sequence number facilitates the flooding and distinguishes LSP from old ones. The fourth age prevents old LSP from remaining in the domain for a long time. So LPS are generated on two occasions. First, when there is a change in the topology of the domain, or second, when a periodic basis the period, in this case much longer compared distance vector. So the timer is set for periodic measurement or implementation. A longer period ensures the flooding does not create too much traffic on the network. So this is about the link state packets. So flooding after a node has prepared by ISP, the creation of nodes of copy of LSP are available within the university. A node that receives an LSP compares it with the copy. It may already, so if they arrive LSP older than 1, so it can discard. Now formation of shortest path tree. So a shortest path tree is a tree in which the path between the root and every other node is shortest. The Dijkstra algorithm creates a shortest path tree from graph. The algorithm divides the nodes into two sets, tentative and permanent, that we see in the example. So it finds the neighbors of a current node, so it makes them cell tentative and examine them, and if they pass the criteria, makes the permanent. Now this is a process. So we start now set the root of local node and move it to tentative list. Now the tentative list is empty suppose. Then we stop. If not, then we can select among the nodes in tentative list the one with the shortest path to permanent list. Add each unprocessed neighbors of last node to tentative list if not already there. If a neighbor in the tentative list with larger cumulative cost, replace it with new one. Now this is a link state from which we can find the tentative list of empty. So in that diagram, we see that there is a topology in which ABCD is a node. So we start with the root A. So set root A and move to tentative list. Move to tentative list. Second, move A to permanent list and add B, A, and C and D to tentative list. Tentative means temporary. Okay. Now third diagrams, move C to permanent and add E to tentative list. Now four, move D to permanent list. Thus we can make the different root as a permanent, different nodes starting from the root as a permanent. Now move B to permanent list, and at last all the nodes are covered. Move E to permanent list. So tentative list is empty at the last. Now this is a calculation of routing table for node A. From node A to A cost is 0. Now there is no next router. For node B the cost is 5. Also it doesn't have any next router. C and D also directly connected with the cost 2 and 3 respectively without any next router. Now E, the cost is 6 through C, through C. So next router is C here. So if you see that The next router is C, that is connected to node E. So this is a routing table for node A. Now this is about the next. So we can start with the path vector routing. Distance vector and link state routing are both intra-domain routing protocols. They can be used inside an autonomous system, but not between autonomous systems. So these two protocols are not suitable for inter-domain routing, mostly because of scalability. So both of these routing protocols become interactable when the domain of operation become large. So distance vector routing is subject to instability. So in the domain of operation, so link state routing needs a huge amount of resources to calculate routing tables. So it also creates heavy traffic because of flooding. So there is a need for third routing protocol, which will we call path vector routing. So path vector routing proved to be useful for inter-domain routing. The principle of path vector routing is similar to the of distance vector routing. So in path vector routing, we assume that there is a one node. Suppose there can be more, but one is enough for our conceptual discussion. Okay. So in each autonomous system that acts on behalf of entire autonomous system, let us call the speaker node. The speaker node in an AS creates a routing table and advertises it to speaker nodes in the neighboring AS. The idea is the same as distance vector routing, except that only speaker nodes in each AS can communicate with each other. However, what is advertised is different. A speaker node advertises the path, not the metric of the nodes. So in its autonomous system or other autonomous system, we see that. So this is the initial routing table in path vector routing for interdomain. So this is a diagram and network is given. So autonomous system 1 is having 5 nodes. Autonomous 3 is having 3 nodes. Autonomous 2 again 4 nodes. Autonomous system 4 again 4 nodes. So each autonomous system in which first initialization is done. So initialization with destination. So destination is A1 and path is AS1. If we start with A1, so autonomous system 1 is a path and node is A1, A2, A3, 5. Both belongs to the path AS1. Now C1, C2, C3, these are the destination. Again, autonomous system 3. So AS3 is given in C1 table. Now D1 table, again it consists of path AS4, that is autonomous system 4, with destination D1, D2, D3, D4. Now destination is B1, B2, B3, B4 for autonomous system 2. So path is again autonomous system 2. So this is a AS A1 stable, C1 stable, B1 stable, and G1 stable. So this is a initialization at the start. Now again second sharing. So that sharing we see that just as in distance vector routing in path, you consider a speaker in an autonomous system share its table with immediate neighbors. Node A1 share its table with nodes B1 and C1. Node C1 share its table with nodes Z1, B1 and A1. Node B1 share its table with C1 and A1 node share B1 share its table with C1 as shown in figure. Now this is a table. This is a table which gives the path A1 to A1 through AS, A5 AS. So AS1 to S2 through path is given for A1 table, B1 table, and C1 and D1. If you want to go A1 to A1 from AS1, you start with the A5 again AS1. If you want to go B1 from A, so there is a path B1, AS1, AS2. So this is a interdomain. So interdomain values are given. Now B, if you want to go B, so autonomous system 1 to be autonomous system 2. So this is a intellectual interdomain path. Now third path part is a now third part is a updating. So when a speaker node receives two column table from a neighbor, it updates its own table by adding the nodes that are not in its routing table and adding its own autonomous system. And the autonomous system that send the table after a while each speaker has table and know how to reach each node in the other autonomous system. So while updating there is a loop prevention. The instability of distance vector routing and creation of loops can be avoided in path vector routing. So when a router receives a message, it checks to see if its autonomous system in the path leads to the destination. If it is looping is involved and the message is ignored. Now there is a policy routing and optimum path. So policy routing can be implemented through path vector routing and optimal path vector routing, where we're looking a path to the destination that is best for the organization. So that runs as the autonomous system. So in policy routing can easily can be implemented. Policy routing. So when router receives a message, it can check the path of the autonomous system So in optimal path, what is the optimal path in path vector routing? We are looking for a path to a destination. We are looking path to the destination. So here there is a one system may use routing information protocol, or we also call hop count as the metric. Another may use OSPF with the minimum delay defined in the metric. In our previous figure, each autonomous system may have more than one path to destination. So, for example, a path from AS4 to AS1 can be AS4, AS3, AS2, AS1, or it can be AS4, AS3, and AS1 for the table. We choose the one that had the smaller number of AS, but this is not always the case. Other criteria such as security, safety, reliability can be also be applied. Now, hierarchical routing. The net. What is hierarchical routing? The routing table grows proportionally, not only the router memory by every increasing tables, but more CPU time is needed to scan them and more bandwidth is needed to send status report about them. At a certain point, network may grow to the point where it is no longer feasible for every router to have an entry for every other router. So the routing will have to done hierarchically as it is in the telephone network. When hierarchical routing is used, the routers are divided into what we call regions. Each routers know all the detail about how to route packets to the destination. So how within own region, but know about the internal structure of regions. So here, for huge networks, uh, two level hierarchy may insufficient. Two level hierarchy may insufficient. So it it may be necessary to group the regions and clusters. So the clusters into zones, if you consider cluster into zones, so the zones into groups and so on until we run out of names for the aggregation. So this is the regions and nodes A1, 1A, 1B, 1C, 2A, 2B, 2C, 2D, region 2, region 3, region 4, region 5. So full table of 1A. If you consider 1A and hops, 1B to reach the 1B, from 1A we needs 1 hops to reach the 1A to 1C, again same 1 hop to 2A we reach 1A, 1C and to 3B. So 2 hops. So count of hops is given uh, in that hierarchical routing. So if you consider a hierarchical table from 1A to 1B, only 1C, so all the nodes 1B, 1A, 1C, 1B, 1C, again 2, 1C, again 3, and 1C, again 4. So this is a hierarchical table for 1A. So when a single network becomes very large, and interesting question, how many levels should be hierarchy? How? So consider a network with 720 routers. If there is no hierarchy, each router needs 720 routing table entries. If the network is partitioned into 24 regions or 30 routers, each router needs only 30 local entries plus 30, 23 remote entries for a total 53 entries. So if a three-level hierarchy is select with the 8 cluster and each containing 9 regions. So of 10 routers. So each router needs 10 entries for a local routers, 8 entries for routing to others regions with its own cluster, and entries for distinct cluster for a total of 25 entries. A common and Klein rock. These scientists in 1979 discovered that the optical number of levels for an router network is n, capital N, that is requiring a total of E in n entries per router. Now, congestion control. What is the congestion? Too many packets present the network causes packet delay and loss that degrade the performance. So, this situation is called congestion. The network and transport layer share the responsibility for handling congestion. Since congestion occurs within the network, it is network layer that directly experiences it and must ultimately determine what to do with the excess packet. So, however, the most effectively way to control congestion is to reduce the load that the transport. First, or so these requires the network and transport layer to work together. So we'll look aspect of congestions. So that diagram, so offered load that is in packets per second. Now packets per second, good put. So capacity of network is given. The ideal value for load compare with the good put. So it is a desirable response and congestion collapse and one set of congestion. When too much traffic is offered, congestion sets in, performance degrades sharply. So in that figure or in that graph, we see that there is a dispatch of one set of congestion when number of packets hosts sent into the network is within the carrying capacity. So number delivered is proportional to the number sent. If twice as many are sent, so twice as many are delivered. So however, as the offer load approaches the carrying capacity, burst of traffic is ordinarily. So fill up the buffer inside. The carrying capacity burst of traffic occasionally. Fill up the buffer inside the routers and some packets are lost. So these lost packets consume some of the capacity. So the number of delivered packets falls below the ideal curve. The network is now congested. So unless the network well designed, it may experience a congestion collapse. So congestion control and flow control. So congestion control has making sure network is able to carry the offered traffic. It is global issue involving the behavior of all hosts and routers. Now flow control in contrast related to the traffic between particular sender and particular receiver. Its jobs is to make sure that the fast sender cannot continuously or transmit data faster than that. The receiver is able to absorb it. Now to see the difference, we consider a network made up of 200 Gbps. So here fiber optics links on supercomputer is trying to force a feed large file to personal computer that is capable of handling only 1 Gbps. So there is no congestion flow control is needed to force supercomputer to stop frequently the queue personal computer to change the to breathe. Now several techniques can be employed for congestion control, that is warning bit, choke packet, load shedding, random early discard, and traffic shaping. So first three with ideal congestion detection and recovery, last two with the congestion avoidance. Now understanding the IP addresses and subnets and CIDR notation for networking. So understanding networking is fundamental part of complex environment on internet. So this has we're trying to communicate between several efficiently, developing secure network policies and keeping our nodes organized. So in see the networking terminology. So every location on device network must be addressable. This means that it can be reached by referencing its designation under predefined system of address in the normal TCP/IP model of network layering. So this is handle a few different layers, but usually when we refer to address on a network, we are taking about IP address. So IP address allows network resources to reach through network interface. So one computer wants to communicate with another computer, it can address the information to the remote computer IP address. So each IP address must be unique on its own network. Network can be isolated from one another and they can be bridged and translated to provide access between distinct networks. A system called network address translation. The difference between IPv4 and IPv6, there are two revisions of IP protocol or versions, we say that. So first is IPv4 and IPv6. IPv6 is slowly replacing IPv4 due to improvement in the protocol and limitations of IPv4 address space. Simply put, the world now has too many internet connected devices for the amount of addresses available through IPv4. So IPv4 addresses are 32-bit addresses. Each byte or 8-bit segment of the address is divided by a period and typically expressed as a number of 0 to 255. Even though these numbers are typically expressed in decimal to aid and human comparison. Each segment is usually referred to as octet to express the fact that is representation of 8 bits. A typical IPv4 address looks like something 192.168.0.5. The lowest value in each octet is 0 and highest value is 255. We can also express the binary to get better idea of how to 4 octet will look. So we will separate each 4 bits by a space of readability and replace the dots with the dashes. So we can replace these dashes. So 1100, 4 times zeros, 1010, 1000, dash all zeros, and 400101. To express this extended address range, IPv6 is generally written out as a 8 segments of a 4 hexadecimal digits. So hexadecimal numbers represent the numbers 0 to 15 by using digits 0 to 9 as well as the numbers A to F to express the higher value. Typical IPv6 address might look something like this: 12038 separated by a colon 8FE0. Now here is the class. If you consider IPv4, so it divides into 5 class IPv4 addresses. So IPv4 address were traditionally divided into 5 different classes named A to E. So these are defined by the first 4 bits of each address. You can find that IP address belongs to looking at these bits. Here is a translation table that defines the addresses based on their leading bits. Class A, first bit is 0. If the first bit is of an IPv4 address is 0, this means that the address part of a class A. This means that any address starting from 0. So this range is given 0 to 127. 0.0.0, 127.255.255.250. Now if class B, so first 2 bits is includes 10, that is address from 128.0.0.2 191.255.250. These represent the address that have a 1 for their first bit but don't have a 1 for second. Class C, 110, class C defined as the address range. So range is starting from 192.0.0.0 to 223.255.255.255. These represent all of the addresses with 1 for their first 2 bits, but without a 1 for their third bit. Class D, if you consider 4 bit is 1110. So this class includes addresses that have 111 as their first 3 bits but 0 for the next bit. So these addresses range includes addresses from 224.0.0 to 239.255.255.250. Now class E, in class E all the 4 bits are 1. So this class defines addresses between 240.0.0 and 255.255.255.251. So any address that begins with 41 bits is included in class E. So there is some reserved private ranges that is given. So most reserve is specify address from 127.0.0 to this range is 127.255.255.2. So this range is used by each host to test networking to itself. Typically, this is express first address in this range 127.0.0.1. Each normal class also have range within them. Is to designate a private net. So for class A address, the addresses from 10.0.0 to 10.0255.255.250 are reserved for private network assignment. So for class B, so this range is 179.16.0.0 to 172.31.255.255. So for class C, the range of 192.168.0.0 to 192.68.255.255 is reserved for private uses. So we start. So this is a reserved private ranges. Now net masks and subnets. So this is our last topic. So the process of Dividing a network into smaller network section is called subnetting. This can be useful for many different purposes and help an isolate group of hosts from each other to deal with them more easily. As we discussed above, each address space is divided into a network portion and a host portion. The amount of the address that each of these take up is dependent on the class that the address belongs to. For instance, for class C addresses, first three octets are used to describe the network for the address. So 192.168.0.15, the 192.168.0.0 portion describe the network, and the 15 describe the host. So for by default, each network has only one subnet, which contains all of the host addresses defined within a net mask is basically a specification of the amount of address bits that are used for the network portion. A subnet mask is another net mask within used to further divide the network. Each bit of address that is considered significant for describing the network should be represented as a 1 in the net mask. So for instance, the address we discuss 192.168.0.15 can be expressed like this in binary. So binary numbers are given here as we described. The network portion for class C address is first 3 octet or the first 24 bits, since these are the significant bits that we want to reserve. The net mask would be, so this can be written in the normal IPv4 format 255.255.255.0. Any bit that is a 0 in the binary representation of the net mask is considered part of the host portion of the address and can be variable. The bits are one are static, however, for the network or subnetwork that is being discussed. So we determine the network portion of the address by applying a bitwise and operation to between the address and the net mask. A bitwise and operation will save the networking portion of the address and discard the host portion. The result of this on your above example that is represent our network is given here 110000 10101 all zeros and all zeros. So this can be expressed as a 192.168.0.0. The host specification is then difference between this original value and host portion. The host is 0001111 or 50. The idea of subnetting is to make portion of the host space and address use it as an additional networking specification to divide the address space again. So for instance, a net mask 255.255.255.0 as we saw above leaves us with 254 hosts in the network. So you cannot end 0 or 255 because these are reserves. So if you wanted to divide the into sub networks, we could use one of bit the conventional host portion of the address as the subnet mask. Let's see so examples. So more, this is example. We use more bits out of host space for networking, and we get more sub networks. So that example is described in that PPT. We can use the first 4 bit of our host to designate and subnetwork we can do by adjusting subnet mask from this. So this would be express though that IPv4 traditionally effectively produces two subnetworks. First subnetwork is range is given 192 to 0.12 192.168.0.127. The second subnetwork contains the host 192.168.0.129 to 192.168.0.255. So traditionally the subnet itself must be used as an address. If we use more bits out of the host space for networking, we can get more and more subnetworks. Thus we find this example of subnetting. CIDR notation. A system called classless interdomain routing or CIDR was developed an alternative to traditional subnetting. The idea that can you add specification in the IP address itself as to the number of significant bits that makes the routing or networking portion. So example is given IP address is 192.168.0.15 is associated with the net mask is given 24 bits are 1 and rest of 0 that is 255.255.255. By using CIDR notation, uh, we can use the address by slash of class bits. So 24, so this means that the first 24 bits of the IP address are significant for the network routing. So thus use some interesting possibility, we can use these two supernets. In this case we can use address range that is possible with the traditional subnet mask, for instance in the class C networks. So we could not combine the addresses from the network. Okay, so because the net mask for a class C address is 255.255.255.0. So using CIDR notation, we can combine these blocks by referencing the chunks as a 192.168.0.0. These specify there are 23 bits used for the network portion and that we are referring to. So the first network could be represented like this. So this is given here. While the CIDR address we indicate first 23 bits used for network block and this is equivalent to net mask. So these bits, as you can see, with the block 24 bit can be either 0 or 1 and match because the network block only cares about the first 23 digits. So CIDR allows us more control over addressing IP addresses. This much more useful than the subnetting we talk about originally. So and there are some network layer protocol that is also included ARP. So address ARP is address resolution protocol use associated with IP address with MAC address. Okay. Now RARP is a reverse address resolution protocol. If host want to know IP address, then broadcast RARP packet contains physical address. RARP server on the network will recognize RARP packet and respond back to the host IP address. So ICMP stand for Internet Control Message Protocol and is used by host routers send notification of IP datagram problem back to the sender. So ICMP protocol reports error messages. So there are 5 types of error handled by ICMP: destination unreachable, source quench, time exceeded, parameter problem, and redirection. Now, what is IGMP again? It is a network layer protocol. Internet IGMP stand for Internet Group Message Protocol. So two types of communication: unicasting and multicasting done by in IGMP. IGMP protocol is used by host and router to support multicasting. The IGMP protocol is used by the host and router to identify the host and LAN that are members of a group. So thus we conclude here with this topic. So here we see that these are the ICP, IGMP, RARP. So it is a network layer protocols. If you see that ARP, RARP. Okay, so we stop here with this last PPT.